Hi everyone, this is M. Pavan from Data Science branch from IRE College. Now I am here to present a presentation about the curse of knowledge in visual data communication. So today we will learn what the things we need to learn about this thing, about curse of knowledge in visual data communication. We will move on to next slides to learn more about this. Here we go. This is the introduction part of our topic. This curse of knowledge is a well studied psychological phenomenon that appears in many domains. Well informed decision makers fail to predict the judgments of less informed decision makers, impl- im- implicitly allowing their own knowledge to guide those predictions. This curse of knowledge has powerful consequences for communication because people generally do not convey information to others if they assume that it is already shared. Presenters must therefore have an accurate idea of what their audience know and do not know, so that they can include only the information the audience still need. Unfortunately, this knowledge is too often not present or not alleged. Even teachers misjudge their students' abilities and understanding, hindering effective instruction. Means the curse of knowledge is one of the main aspects in our life that, well, the decision makers are unable to understand what the speaker is explaining, in what the motto of he explaining, and what are the intentions to, and what are the motto of his explanation. Nowadays, most of them are not understanding, are not at all predicting the what are the decisions taken by the makers on what aspects, and what are the things they are considering to take those decisions. So we will learn more about this decision taking and the curse of knowledge in our further slides. Well, the curse of knowledge is well studied in the psychological of language, decision making, and reasoning. There is less direct research on potential consequences for communication with data visualization. The present experiment demonstrates that different experience with a dataset can cause people to adopt a particular perspective, which can subsequently change their predictions about what native viewers will find slight in a visualization. So in this PPT, we are going to present an experiment that have a different experience dataset can people to adopt a particular perspective, which can subsequently change their predictions. Means most of the people predict their own things in one of the similar idea. So we will understand the different experiences in with this dataset. Given the primary role visualization play in the communication of analytic data across science, education, and industry, focusing on different patterns in the same dataset harbors the potential for miscommunication between the presenters and their audience. So, for this curse of knowledge, we have some related work. The curse of knowledge can also occur within a single person in the form of Hinson bias. This bias studied in business decision making, political strategy, and marketing is the irrational belief that an outcome was more predictable after it becomes known. The curse of knowledge can also particularly strong effects in children who have more trouble inhabiting their own knowledge. Means apart from the other audience and the motives, there are some other things that are affected by the curse of knowledge within a single person. That may be a business decisions, or political strategies, or marketing, like so on. So in the same way, the curse of knowledge is also have showing so much effect in children who have more trouble in their own knowledge. Visualization researchers have recently become interested in decision biases. For example, the attraction effect, which is a cognitive bias where irrelevant information can influence decisions about otherwise equal alternatives, can influence decision making in visualized data. Here we are going to see one experiment. In this experiment, we will learn, we will observe the dataset of different experiences of the people, of their mottos or of their respective ideas in this. We tested the hypothesis across 4 experiments. Experiment 1A provided the participants with background knowledge as well as summarizing graph with visual annotation to emphasize the primed graph features. Experiment 1B tested further the effects that would hold when visual and visual annotations were omitted. Experiment 1C instructionally isolated participant predictions to only certain types of graph features. Finally, experiment 2 tested the generalizability of this effect with a different type of graph and a different set of stories. So in this one, we will need to know the importance of all these things, and we will further discuss about the experiments 1A, 1B, 1C, and the experiment 2 tested the generalizability of this effect. So we will move on to next slides to learn more about it. So here we are. We are going to see the first experiment of our throughout experiments. Line graph experiment 1A. Participants. Eastern 18th Northwestern University students participated in this experiment in exchange for course credits in an introductory psychological class. All participants were asked to bring corresponding eyewear if needed. So our experiments are taken in Northwestern University are taken by the Northwestern University students. They are 10 women. In the 18 Northwestern University, it happened. So we will come to know how the experiment happened and what are the things they learned and what are the things they are going to give us. So we will move on to learn how these things are happening and what are the things we need to focus. So let's move on. Graph. In our experiment, we are going to show the dataset in a graph method. So the variations in the graph can give us what's happening and what the things they are considering in these graphs. So when participants predicted what an uninformed graph viewer would see as the most visually slant features of the graph, where they're shown an unautomated version of the line graph. They were told that this annotated graph was all that the uninformed graph viewers would see. Paper copies of this unhighlighted graph were provided to the participants to mark down their 5 predictions separately. We also conducted several plot versions of this experiment where we tracked the most salient features regardless of what was primed and adjusted its appearance to accommodate those salience values. Example, by making a peakless shape or a color differ stronger. This what the participants are predicting is uninformed graph viewers. So they are shown an unauthorized version of this line graph. They were told that This uninformed graph was that all the uninformed graph viewers would see. Paper copies of this non-unhighlighted graph were provided to the participants. So we will see what the participants are going to do about all these things. What are they going to predict, or what are they thinking of what happening? So we will discuss about this in our further slides. Matching futures. The participants then matched their own predictions to the 5 predetermined futures, referring to their marketing on the paper copies of the unautomated graph. Participants referred to their freely identified slant future drawings and matched them with the 5 futures mentioned. If the future they draw does not match any of the 5, they indicated it as NA. NA means not nothing. The subsequent quantitative data analysis of the SLASI predictions and rankings were done on the rankings of the 5 predetermined futures. Among the 5 predetermined futures, 80%, 48% matched with the participants' freely identified slant futures drawings, and 56% matched if we only look at the participants' top 3 predictions. So we will move on. Qualitative results. In our experiment, we are going to see what are the qualitative results. Examining what the participants marked down on their physical copies of the unautomated graph, we have qualitatively observable differences among the 3 story versions. We see that depending on what version of the story participants read, free predictions reflected that they thought other uninformed viewers would see the futures highlighted in their particular story as visually slant. Even though participants were explicitly told to ignore the story when making their predictions, the participants who read the mid-prime story identified global and mirroring futures to be slant to other viewers. Notice how participants often circled pairs of futures spanning a large area, as opposed to local futures identified by participants who read the top and bottom prime. Quantitative results. Using the data from the future, making session of the experiment ranking were assigned to the 5 predefined futures. If a participant does not think any of the 5 predetermined features match to one of the predictions, the specific prediction could be matched as NA. The ranking spot of this prediction would be counted as taken. We conducted a non-parametric Volosin-signed rank test comparing the participants' SLANCI rankings of primed futures and not primed futures. Primed future rankings are rankings of futures highlighted in the story the participant read. Okay, we will move on and we will discuss about the further experiments to learn how the participants are participated and what are the predictions they have taken in their experiments. Discussions. The knowledge the participants obtained by reading the story biased their predictions such that in general they saw the futures depicted in the story as more visually slant than futures not depicted in the story. More importantly, after acknowledging this background knowledge, participants were biased to predict that other uninformed graph viewers would rate these futures as more visually slant as well. Both qualitative and quantitative statistical analysis for this experiment were done post. To ensure the validity of our findings, we conducted 2 follow-up experiments with slant modifications with a new set of participants and analyzed the data following similar predictions producers, and an identical data analysis. Now we will discuss about the line graph experiment 1B. Experiment 1B hoped to tease apart the priming effect of the visual attenuations and that of the story by only including the story and removing the graph visual highlighting the story. The procedures and the data analysis of experiment 1B were identical to that of the experiment 1A, except we removed the futures cause after viewing the story. The participants read the story and were presented the same unatonated line graph to draw and predict what other uninformed viewers would see. We hypothesize that even without the visual cue, the participant would be just as biased in predicting what others informed viewers would see. Think they would see the same features as visually slant. Quantitative results. We also observed an interesting change in the middle prime saliency prediction from experiment 1A to 1B, such that the experiments in 1A were primed with the middle feature rated is slightly more visually slant than participants in 1B. We speculate that while background story and visual attenuation both contribute to the cause of knowledge, as shown in experiment 1A and 1B, for spectrally separated features, the visual attenuation may play a small influential role in creating a curse of knowledge effect. This indicates that even without the visual attenuation clue, the more visually slant a future participants rated to themselves, the more visually slant they think the futures were to a native viewer. So about we will discuss about this. We observed a statistically weaker curse of knowledge effect without the visual attenuation in the present experiment. However, most participants nonetheless reported features primed by the story to be more visually slant than features not primed by the story, even without visual attenuations. This suggestions that only have the background knowledge without any visual attenuation clues, it is still enough to bias people to predict that other native graph viewers would see features primed by the story as more visually slant. So, so from these experiments and from our knowledge, concluding this topic, across 4 experiments and the 2 types of graphs, it is clear that participants are susceptible to a curse of knowledge when asked to simulate what others could see in a visualization. To our knowledge, this is the first empirical demonstration of the curse of knowledge in the realm of data visualization, and even in the broader realm of visual perception. This result joins other ascent explorations of the influence of perspectual and consecutive basis on interpretations of predictions in the data visualizations, may of which cannot be easily intimidated. Some of this research has begun to explore visual designs and interactive making, decision making environments that migrate these biases. So, thank you for giving me this wonderful opportunity to share my knowledge with you. I hope everyone having a great day. Thank you all.